Hello everyone. Alright, welcome back to CMSE 203. Alright, let me kill that. Alright, sorry about that. Okay, so let's review a few definitions first. And I guess there's a few like administrative things. So let's talk about administrative things. Somehow I suspect if I had an echo, you would learn everything 1/2 of a time rather than one time. It doesn't scale linearly. So exams. I have graded 4 so far. So that's not good, not great. But I am working on it. I need to get my workflow settled for exam grading to speed up the process just a little bit in order to kind of push through. Oh, I shouldn't say not great as in you. I should say the exam scores have been, the scores, pretty good. This is not great directed at me for my lack of progress. This is not great directed at you. Okay. Yeah, it's a workflow issue because it's a bit of like, I just figured out how to download all of them as a group out of Blackboard, and so will there be a curve on the exam? Curve. I don't know. So what will determine whether there will be a curve is if there's a significant deviation in people's exam grades, some kind of thing. My suspicion is probably not, but I'm just saying that to protect myself. If I want to give you guys a curve, I will. Maybe I should mention this about grading in the class. I am aware that there are other versions of this class where the material that's covered is relatively minimal, and so my goal here is that no one should be punished, right? For ending up in this section. So that's kind of my general philosophy currently. Okay. I mean, everybody really did well on exam 1, and I actually think people are doing pretty well on exam 2. If anybody really tanks exam 2, then, I might do something about that. So don't worry too hard about your grades. Hopefully, is there an annoying background noise? I don't know. No. Can I give an update on how grading percentages will be done? I think we're just going to do it in strict point values. So this course is basically going to default to almost total exams. But yeah, the points that you got from, well, maybe I can keep those grades, and basically it'll just count as a gigantic curve. If I do that, because we haven't had any homeworks or quizzes. Why don't we, at the end of this week, I'll check out all your averages. Okay, I don't know. See, I wear headphones, so I'm not entirely sure what that noise is. Let me see if I can hear it when I listen back to the stream. Yeah, something was rubbing against the microphone, and I moved it. It was just a paper towel. Anyway, that is totally irrelevant. Okay, so I'll tell you what, guys. I will calculate grades and give people back like a... Well, I don't wear a mask in my own office. Anyway, maybe I'll give you guys an idea towards the end of the week. I don't want to overpromise. Like, I could say I could give you guys an estimate tonight or tomorrow, but then I know that's just lying, because tonight I have to do... I have to finish the 201 project and release it. And after that, I have to basically get a bunch of 201 grading up and running. And then I have to grade your 203 exams. And so I'm gonna, let's just say towards the end of the week. So Thursday or Friday, maybe we'll talk. Yeah, I know, I hear you, but the problem is that the quizzes are locked in my office, and I haven't been back to campus since spring break, right? So I know that those quizzes would be helpful. I intended to enter them, over spring break, but it just didn't end up happening. So I probably will have to go back to campus. Well, so I'm technically sort of allowed to go onto campus. I think I have to email the department chair and get special permission and talk to the police and all that stuff. So there's special permissions in order to get onto campus. And I'll just have to go through that at least once in order to get them. I mean, I'm going to pretend like it's an essential activity, right? Plus, I mean, I'm not going to see anyone. I'm literally just going to walk into the office, pick up the quizzes, and leave. But it just hasn't been done yet. Yeah, so the only word on the street is that I have to swipe into the building. And if I swipe in without getting permission, I hear that they revoke your permission during all of this corona stuff, so you can't get back on again. So basically, they tell you have to do it right, or you can't come back. So anyway, all right, so that's enough administrative stuff. Let's talk about probability a little bit. So this is the definition of conditional probability again. So if you remember what conditional probability meant. Yeah, I mean, I generally wear gloves and a mask now. It's bad business, really, people. It's bad business. So if we have the probability of B given A, what this means is that we're assuming that A is true. So nothing out here matters. And this part of B doesn't matter. So all that matters is the part here. So we can redraw it a little bit bigger. And here's the part of B. And so that's why this thing is what it is. It's saying, because this part of B happens to be known as A intersection B, and this thing is just the set A. So basically what we're doing is we're saying how much of A is also B, right? That's kind of what we're asking. So because we're asking it in terms of how much is A, that's why we divide by the probability of A so that we scale everything up. What this is doing is scaling up so that if A intersection B is all of A, the probability is 100%, and this is the part of A that is also in B, or the part of B that is also in A. I guess both sentences are true. Okay, so let's just look at Bayes' theorem again, and I want to draw a little picture that I didn't draw last time. I forgot to draw this picture. So here's a big picture. So here's our sample space, S. You can also call it the universe U. It doesn't really matter. And remember that these sets B1 to Bn are mutually exclusive. And so mutually exclusive means that Bi intersect Bj is equal to 0. Or perhaps if you want to be very technical, you can say the probability of that is equal to 0. I should say that the Bi intersect Bj is equal to the null set if I is not equal to j. Yeah, I wonder how many people watch that cartoon. I actually haven't seen it. I'm an old man. So anyway, I'm going to draw some squiggly lines. Hopefully nothing terribly confusing. Okay, so in this case, we're going to have, say, B1, B2, B3, B4, B5, B6, and B7. Now you see that they're all mutually exclusive, and they all add up to the sample space. So the union of BI is equal to the sample space. So basically, what Bayes' theorem says is this. So let's take A as some set that kind of does this. It's like some sausage, right? Some sausage set A. So the idea about the set A here is that if you let's look at the formula and see what it means. So we want to know the probability of say BK. Let's just make it B4 given A, right, is equal to, and then so the thing is that say we don't know this number here, but if we know the probability of A given, say, B4 times the probability of B4, then we're good to go. Now, all we have to do now is divide by this horrible, messy formula, which is the probability of A given, say, B1 times the probability of B1. Now, really, you can actually rewrite all of these as intersections. So this is the probability of A intersection B1 plus the probability of A intersection B2 plus a dot dot dot, which plus the probability of say A intersection B, and we're only going up to 7 here. So whoops, that's not right. Okay, undo that. Cool. 7. There we are. So the idea here is that means that we could get the overall probability. Yeah, we could choose any of the 7 B's. So yeah, B, the K is just means it's something in this case, it's just in 1 through 7. But so in general, K is in 1 through N. So the point here is what are we asking for? We're asking for, given that we've ended up, so basically you have to imagine that this is a big dartboard, or something like that, and you've shot a dart at the dartboard and it's landed, say, here, right? Or maybe it's landed here, right? So this is, it landed in A, and so you know it landed in A, so that's what given A means, right? Given it landed in A, what's the probability that it ended up in B4? So here, it could have ended up anywhere. So it could be, for instance, you could have one here, or you could have one here, or you could have one here. But none of these other dots here are good, right? These are all bad dots. The only good dot is going to be the, I guess, green dot. The green dot is the good dot. And the reason why it's the good dot is because it's the one that ended up in A. So now all the darts that land outside of this, you get to reshoot. So basically you reshoot them until you have some of them that land in various sets, right? Like this. And now your question is, given that it landed somewhere in this weird blobular set A, what is the probability that it landed specifically on this strip B4? And so that's kind of the question you're asking with Bayes' theorem. And so Bayes' theorem, as I should say, is really, I mean, a topologist or something might say it's like it's a law of commutation. It's a way that you can swap these two symbols. So that's really what it is, because you see here, you have to know all of these symbols here, where A given B1, A given B2, A given B3, A given B7. Here, this is the probability of, given that it landed in A, the thing that you don't really know much about, what's the probability that it landed in, say, B4? So that's kind of I think this is a better explanation than the explanation I gave before. As it turns out, I just remembered it, and I was like, oh yes, this is definitely a way better explanation. So, okay, so basically it's a way to swap symbols. If you have a symbol you know and you have a symbol you don't know, then you can swap them around and get the other one. Okay. Oh, yo. Well, I'm lecturing. I'm about to unmute my desktop audio so they can hear you. Right now, it's me talking to myself, which is, I guess, not completely abnormal. All right, go ahead.
You guys were talking about Steven Universe? What?
Someone mentioned it. Well, because I said, I have a fundamental belief that there's not really such a thing as probability theory. It's all just set theory. And so in set theory, they call it a universe, and in probability theory, they call it a sample space. So I wrote S equals U.
I see.
Which, at least I didn't write Susie, right? S-U-S-Y.
Oh, yeah, that would have been a thing.
Which is supersymmetric supersymmetry, right?
Anyway, Steven Universe, really good show.
Yeah, I've never seen it.
Oh, love it.
So I just wrote this definition of ooh, and then I crossed it out. Okay, try again. I wrote the definition of independence again, and I copy-pasted it, so I again forgot to change that to a multiplication sign. Okay. So this is just another fact. This is just like a recall from previous lecture. Previously on Math 203 or cs203. And so the one thing I do want to say, and I do want to remind you guys, is remember that mutually exclusive means that the probability of A intersection B is 0. And so remember that independence just means that the two things don't have anything to do with each other. Mutually exclusive actually means that they have everything to do with each other, because if one of them happens, then the other one can't happen. So they're not independent when they're influencing each other like that. So usually, unless of course the probability of A is equal to 0 or the probability of B is equal to 0. If this is not true, if I guess not this, then basically mutually exclusive is not equal to independent. And it's just a bit of terminology, but it's terminology that I found that everybody, when I used to teach probability, would just start, they would say like, oh, something's independent, therefore, and then they would remember the probability is 0, or they'd get them mixed up. So, so mutual exclusivity is not independent, is generally not independence. Okay. And so, so this question is really, if A intersection B is the empty set, then what must be true for them to be independent? I've actually written the answer to that here. So in order for two mutually exclusive events to be independent, the probability of A is equal to 0, or the probability of B is equal to 0. So, surprise. What does the right hand say? The equation of the definition. Right hand side. Oh, this is just the probability of A times the probability of B. I tend not to use the X symbol for times. It makes me feel nervous. Okay. So here's something we can do.
I have a question.
Sure.
It's an actual question.
What?
So what is it intuitively, like, what does it mean when the events are independent as opposed to mutually exclusive? Means they have like,
well, maybe the students can answer that
together.
Yeah, so I mean, independence is a bit more complicated than mutual exclusivity, in the sense that it's always easier to say if A happens and B doesn't happen, or if B happens, A doesn't happen.
Yeah.
But independence, as I say, is when two events don't influence each other. And it's a little complex to say what that really means. Generally, what it means is like if you flip a coin and then someone flips a coin in another room, right? Those two events don't influence each other. Even if you flip a coin and then you flip another coin, if you assume that you're a fair coin flipper in some sense, then those two events should be independent, because the first coin flip doesn't, like, if you knew that the first coin flip was a heads, what does it tell you about the second coin flip? Nothing.
Right.
Theoretically, unless it's an unfair coin or some, assuming all the natural probabilistic assumptions, what we assume is that the first coin flip doesn't affect the second coin flip. If you roll a die, right, and it comes up 2, and I ask you, okay, take a bet what's going to happen to the next one, and I don't tell you that it was a 2, and you say, I think it's going to be a 4, and then I say, but the last time it was a 2, right, theoretically, that, shouldn't influence your decision-making process, theoretically, if you believe in the fairness of the die and all the other probabilistic assumptions, right? So it's...
Probability of A given B is the same as probability of A.
Yeah, so that's another way to say it, is that the probability of like a coin flip coming up heads, given that the previous one came up heads, is just the same thing as the probability that the coin flip came up heads, right?
Yeah.
I mean, I've said that and written it down once or twice.
Oh, I'm sure you have. I'm just making sure it makes sense to me.
Yeah. I mean,
I'm trying to wash my brain of all I know of this, which isn't hard because it confuses me endlessly.
Yeah, independence is a very... It's a nuanced kind of thing, right? Because, I mean, technically, two events can sound like they're independent, but they're not. Like, I could say, like, what's the probability of, like, a car accident given that, say, it's raining or something? And now, I mean, that sounds a little more obviously probably dependent, but it's like, it's probably not just equal to the probability that someone has a car accident on a given day, right? Because probably if it's raining, the chances of an accident are slightly higher on average, so, you might say something like, okay, the probability of a car accident given that it's raining is higher. So, therefore, these events are not independent because raining influences car accidents, right?
Mm-hmm.
But, of course, a lot of things in statistics, you don't necessarily know if they're independent or not. For instance, in a lot of like, drug trials, right? So, there's, like, the probability that a patient recovers given that you gave them the drug, and then there's just the probability that a patient recovers, right? And the question is, did the drug do anything, right? Is this not equal? Did the drug hurt them, or did the drug help them, or did the drug do nothing? And that is, like, the fundamental question in medical statistics, right? Is, like, this exact equation right here. All they really try to do through double-blind trials is try the best that they can to eliminate as many human causes of error in this equation. What if the probability of recovery given drug is less than the probability of recovery? Well, then the drug was poison, right? It hurt people. Well, I mean, and so we've seen some of that recently, actually. Some recent instances where I think the CIA told people not to take that, hydrochloroquine or whatever it is, because they actually determined that this was the case. This less sign was the case. If you took the drug, you were less likely to survive. So... Anyway,
that's good. I like that. So mutually exclusive means they can't happen together, and independent means the happening of one has no influence on the other, which is like kind of opposite, like you were saying, because if the one thing happens and the other thing can't happen, so they're not independent,
then they're extremely dependent.
Yeah, they're battling. You know, they're like Batman versus Superman.
Sure.
Yeah.
Well, let's not roid rage out like Ben Affleck did. So.
Yeah. All right. Sorry. Anyway, I'm feeling good about this. Let's forge ahead.
Yeah. So let's prove a little fact. This is a simple proof. So if A and B are independent in a sample space S, then what do we know? We know that the probability of A intersection B is equal to the probability of A times the probability of B, if it'll write. Probability of B. And this is just by the definition of independence, right? So what does that say? Then A complement and B are independent. So are A complement and B complement. So let's fix this one first. So what about the probability of A complement intersection B? So the thing is that we actually don't really know anything about this, but I do know something about this. Probability of A union A complement intersection B. Right? I know something about this. And what do I know? I know that, let me see if I can erase more of this crap. So I know that A union A complement is what? Right? So this is equal to the whole sample space. So the sample space intersection B is just equal to B. So this thing is equal to the probability of B. All right. So I want to make an argument here. Now I want to say, okay, now we're going to do some business. Now we're going to say that this is equal to the probability of A intersection B union A complement intersection B by the distributive law. And then what I'm going to do, finally, is use the double union formula. So this is by the distributive law for sets. And now I'm going to use the double union formula, which says that this is equal to the probability of A intersection B, B, plus the probability of A complement intersection B, which is the thing we're interested in. This is what we want. And so technically there's a subtracted term minus the probability of A intersection B intersection A complement intersection B, if this thing will write. Well, the good news is B intersection B is B. A intersection A complement. What is A intersection A complement? That's a good question.
Is it all the things?
A intersection A complement.
Oh, it's none of the things.
Yeah, null set. So then what is null set intersect? I was taking a swig of Mountain Dew, so had to recharge my batteries.
Yeah.
So null set intersection B is null set. And the probability of null set, if you recall from our definition of probability, is 0. Beautiful. Beautiful, right?
Incredible.
So the good news is, look at all this complex garbage. Just don't even pay attention to it, right? All right, cool. So now what we know here, we need a new page. We have that the probability of B is equal to the probability of A intersection B plus the probability of A complement intersection B. So this is true. And we know that this is independent, so this is equal to the probability of A times the probability of B, right? We can break up the intersection as this thingy. And so now we subtract. So now we get the probability of A complement intersection B is equal to the probability of B minus the probability of B times the probability of A. Nice. So the last thing we want to do is we want to factor this out. So we want to say this is the probability of B times 1 minus the probability of A. Now, what is...
Ooh,
yeah,
I know.
get ready.
I know.
Get ready.
I know.
What is the
I know this one.
probability of a complement? Huh? What is it?
It's 1 minus the probability of A.
That's right. It's 1 minus the
Booyah!
probability of A. See? Excellent, excellent. So the good news is that we have just shown that, as it turns out, this is the probability of B times the probability of A complement. So that was a little bit of a technical proof.
That's a little whirly-giggers. Now, where's the magic on this one?
Where's the magic?
Yeah.
I don't know, man. Let's look at it. Let's look at it. It's kind of.
I got to admit, it's one of those proofs where like I followed you the whole way, but then when I turn around, I'm like, how did we get here?
Yeah. So I think one of the things that you have to keep in mind about this proof is that it's like one of the follow your nose proofs. So if this is a nose, you have to follow in that direction, right? And so. That's what my advisor always told me, is that some things are just follow your nose proofs, and this is a follow your nose proof. I think the only trick, the only magic here, is that you randomly have to invent.
That's where I was like, that's the brain. The brain happened there.
So you have to invent that this thing where you say A union A complement intersection B, and then just like you have to invent this thing and just play with it until it works, right? Because this term here is not equal to this term, right? Because we've unioned an A onto it. Basically, you start out with the probability of B, and I think this is the trick. The trick is just to start with this. If this was like a test question, which this would be too hard for a test question. Now that I've done it, I didn't know how hard it was going to be until I actually did it. So probably too hard for a test question. But the good news about it is that this is the trick.
What if you like replaced? Oh no, you can't do that. Never mind.
Okay. Yeah, I mean, I don't know a simpler thing to do than this. This was, I would say, pretty simple, right?
Yeah.
Never mind. I guess I'm
kind
wrong.
of thought it. I thought maybe you were gonna do like a proof by contradiction or
something. Evidently no. So I didn't. Here's the thing: when I started the proof, I didn't know what I was gonna do. But then I looked at this symbol, and I thought to myself, I don't know anything about that, but I do know something about the probability of B. And I know that I can always break things up. I can always say that the sample space is equal to A union A complement.
Oh.
And I know that the sample space intersection B is just equal to B. And so I took these two ideas and just plugged them into the proof.
I see. That's where you got your... So you basically were like, how do I get an expression?
How do I get the expression that's in this box right here? This probability of A complement intersection B.
Yeah.
And the only thing we're allowed to end up with is the probability of A times the probability of B, because that's the only assumption, is that A and B are independent. Right? And so that's why I said, well, we need to depend on A somehow. Right?
Cool.
Yeah, I mean, it's a proof. As I say, all proofs, well, most proofs have at least one of these, like, tricks in them. Okay, so here's a problem I stole. I stole every problem. I found a book, and I stole problems from it. There weren't really enough problems in our book about Bayes' theorem, and I think Bayes' theorem, the thing about Bayes' theorem is that it's extremely useful in like neural nets, in NLP, in general life. You know, when you're making decisions, like, it's just useful, and so going through it isn't a bad thing. And doing a ton of examples of it is pretty good.
I can say that it is very practical.
So what I'm going to do is I'm going to draw some kind of tree here before I even read the problem, because I read the problem before. Here's the tree. Okay, now how am I going to fill in this tree? So, oh God, even when a gizmo-making machine is working in good order. It occasionally malfunctions. Okay, each gizmo... So this sentence can be crossed out because it has no semantic content. Each gizmo made has independently a one... Oh, wow. It's not me, it's the sentence. I blame the sentence. Each gizmo independently has a 1% chance of being defective. That's a better sentence. I didn't write it. Don't blame me. So each gizmo has a 1% chance of being defective. A certain gizmo making machine has just had a new part installed. The first gizmo it makes is defective. Okay. So we know that we're going to make a defective gizmo. It is known that 1 in 50 new parts installed is a dud. So when a dud is used in a gizmo making machine, only 10% of its output is usable, should the new part be replaced. So this is an opinion question.
This feels like the Monty Hall problem.
Thank God, no.
Okay.
Simpler than that.
That's another conditional probability.
Yeah, it is actually.
Have you done that in this class?
I haven't done that in this class. I guess we could do it. I mean, yeah, right? If you just...
I love it because it...
We'll do this problem, and then we'll do the Monty Hall problem.
Yeah. I'm
So,
excited about this one. My opinion, I think we get rid of it.
Okay. Yeah, so each gizmo independently has a 1% chance of being defective. So, okay. 1 out of 50. So either the part is a dud or it's not a dud, right? Not dud. Okay. So there's a 1 in 50 chance that it's a dud. There's a 49 out of 50 chance that it's not. Okay. Hey now. I actually kind of like this problem. And, well, never mind. I did sell my soul about 15 years ago. So, okay. So, and then either the gizmo, right, is defective, so the gizmo is bad, or the gizmo is good. The giz good. So this is bad, and this is good. Good gizmo. If Gizmo were a dog, they would be very happy. Good gizmo. So it is known that when a part is only 10% of its output is usable. So when you have a dud, what that means is that 90%, up here, 90% will be bad, so 0.9, and 0.1 will be good. So each gizmo, even when a gizmo machine is in working order. Okay. So what that means is that given, let's erase this much. So when a gizmo machine is in good working order, it still has a 1% chance of being defective. So that means that if the part is not bad, there's still a 0.01 chance of it being bad. There's a 99% chance of the gizmo being good. So now, when a dud, so what has happened? So we are looking for the probability that we have a dud given a bad gizmo, right? And so the thing is that if we look at all the stuff that's on this tree, we see here that this is the probability of bad given dud, right? B given D. This is the probability of a good gizmo given dud. This is just the probability of dud. This is the probability of dud complement. This is the probability of bad given dud complement. This is the probability of good given dud complement. Well, okay, I've just labeled everything. None of them is this, right? None of them is this one. And so what we have to do is we have to flip these around. So you know that this one's on the tree. So what we can say is that this is equal to the probability of, now we get to flip them, bad given dud times the probability of dud. Divided by probability of B given D times the probability of D. And now, actually, unfortunately, B is our set A, if you remember from the definition. So this is the set A from the definition of Bayes' theorem. Dud is the BI's. So this is B1 here. And unfortunately, dud complement is B2, right? So that's how it matches up with the theorem. Yeah, I think this problem could use a bit of proofreading too, but I didn't have time. I was just copy-pasting them desperately to get this done for the lecture. So bad given dud complement times the probability of dud complement. So that's what we get. The most standard-looking two-term Bayes expansion. Wonderful. So let's compute. So the probability of dud is 1 out of 50 times the probability of this, which is 0.9, divided by the same thing. Notice that you're always going to get the same thing as one of the terms in Bayes' theorem on the numerator and the denominator, because as it turns out, this term is going to be one of the BKs. Plus 49 out of 50 times the probability of a bad thing given dud complement, which is this one, 0.01. So let us calculate together. Feels very religious. It's, let us pray together, let us calculate together. 0.9 times, oh, you know what we can do instead of, we could multiply, if you're lazy, you can multiply the top and the bottom by 50. And that way you only have to do a simplified calculation. If you're putting this into a calculator or something, reduce your probability of error by doing this. 0.9 plus, and then 49 times 0.01 is 0.49. So this is just 0.9 divided by 1.39. And so those calculations you can do without a calculator. And then this last one you probably want a calculator. So 9 divided by 13.9 is equal to, the final answer is, drumroll please, 64.7%.
Oh yeah!
So what does all that mean, right? What does it all mean,
right.
Basil?
Get rid of it!
Yeah, so as it turns out, the probability that you just replaced the part in the machine with the bad part being the cause of the bad output is over 50%, right? And so what that means to us is that we would probably replace the part again, right? You would probably replace the part again. Maybe you would allow it to make another gizmo, right? If you did that, oh, that's a good question. Maybe we'll come back to that. That's a great question.
That is a good
What happens if you allow it to make another gizmo and it's also bad? How much does the probability increase?
Levels to your tree?
Yeah, you would add levels here and you would add levels there, and
can I see your pointer? I think I can only see when you draw today.
Well, I'm just drawing them in. So
that's true. Okay.
You just have to wait. Yeah, I mean, technically you can add stuff with the good, but you're actually never going to use that side of the tree, so you don't have to. Yep. Wonderful, isn't it?
That's beautiful.
I mean, so I think that there's actually something kind of, I don't know, elegant about these problems.
Monty Hall?
You want to do Monty Hall?
I love Monty Hall.
All right, let's do it.
Because they're going to get in a flame war in chat. I think.
So you'll have to remind me. So there's 3 doors, right?
There's 3 doors.
And there's 1 car and 2 goats.
2 goats. Okay.
Okay, and so, what am I thinking? Wait.
So
Yeah, you pick a door, right?
pick a door.
Yeah, you pick a door. So the rules are, so here's the 3 doors.
Oh, you went with like circle toppy doors.
That's right.
Doors.
That's right.
Very like
Behind 2 of the doors are sheep or goats. Or sheep. What do goats say?
That woke some students up, I'm sure.
Oh, you're welcome. Wow, that's I don't know. I don't think that's a goat. So I'm gonna label it as a goat.
Okay.
There we are.
But you don't know where the goats are.
But yeah, you can't see behind the doors. This is all invisible to you. And of course, behind here is the most sporty car in the history of cars.
Woo!
Sporty car.
Woo! Such a good car.
So the rules are, as you were saying, you pick a door, right?
You pick a door.
Pick a door.
And then they open one of the doors you didn't pick.
Yeah, they open not just any door, but they open only a wrong door. So
and
let's
a goat.
So you pick a door, and then Monty Hall, right? The what do you call him? The host. Wow, I just like forgot a word.
Yeah, then the host will show you a goat behind a door you didn't pick.
A goat door.
Yeah.
And then asks you.
And then you have 2 doors.
Do you swap?
Yeah.
And so...
Right, chat, swap or no swap? Do you swap? Do you not swap? Do you stick to your guns? Do you swap?
He really wants to know. He wants to know. And
I gotta know. Swap? Ooh, 2 swaps.
You know what you should do? You should make one of your little quizzes.
He's just going for the goat. He's like, I don't want a sporty car. I want a buddy. No swap.
Pick the goat. Well, go. Yeah, I guess if you're...
Pick the goat. Because they could have lied to you. And the door actually has, like, bees behind it.
No such thing exists. There's no bee door. Okay.
No bee door. It's cool.
Yeah, okay. Goats are the weirdest things, though. Has anyone ever seen a goat's eye?
Yeah.
Goats' eyes are like dumbbells. They have these weird things in their... It's like a dog bone.
They're kind of they're
it's like a barbell dumbbell kind of shape.
Apparently, I've read that the hypothesis is that it gives them a better field of view when they're grazing. But then I don't quite 100% buy that.
No, I think that goats are just...
When you look at a goat's eye, though, you know not much is looking back at you.
I think goats are just weird. Okay.
So we've gotten some...
No, so yeah, why don't you make yourself a quiz and give them a link to the quiz?
Oh yeah, let's do that.
And then and we can give them the quiz and they can answer it while we are solving the problem. And then at the end of the problem, they can be like, "Oh crap, I picked the wrong thing. I should have done whatever the answer is." So let's do it. Okay.
Vote now.
Yeah.
Dial on your phones. Swap or no swap.
So. Okay.
The door shown to the guests is not the door they picked. Correct. So you pick a door.
Yeah. So they pick a goat door that you didn't pick.
Yep.
So I think it's useful to just go over some examples of what can happen. So for instance, let's say that, car is always behind door A and goats are always behind doors B and C, but we don't know that coming in the room, right?
It is neck and neck 4-4 right
Yeah.
now.
So let's say I pick door B, right? Then the host has to show me door C because they can't show me door B because they want me to potentially be able to stick with my door, right? And if they said, oh, there's a goat behind door B, then obviously you would swap to A or C. But you don't open the door. No, you pick a door, but you don't open the door. You don't know if... So I'm going to say door B, right? And then Monty has to show me door C, right? And then I get to swap or not. So then I get to swap or not. And so if I swap, then I obviously pick A. But if I picked A first and he shows me door C and I swap, then I pick B, the goat door. So, yeah. Okay. Would it be easier to say the host makes it so that it's 50? Yeah, in fact, that might or might not be the case. So let's draw out a tree.
Let's see what do we got here. Oh, no swap is in the lead by 1 vote.
Okay.
6-7 right now.
So what are the things that happen? So you pick a door, and so the probability that you pick the car, right, is 1/3, and the probability that you pick a goat is 2/3, right? But, and now here's the thing. So here's the swap or say that this is the non-swap, right? And here's the swap option. So here's the thing. If you know, so here's door A, door B, and door C. And so I pick door B, but I don't know if there's a car or a goat behind it. So Monty shows me door C, and there's a goat here, right? And then I elect to swap, right? So well, if I elect to swap, then actually what I'm doing is I'm choosing 1 out of 2 doors, right? And so there's actually a 50% chance that I get the car, and a 50% chance that I get the goat. So, yeah, so the Monty Hall problem, I guess, how should I draw this out where it makes better sense?
It's tricky.
Yeah, I'm trying to think.
I have a very good intuitive motivation for it, but I forget
So-
the actual dealings.
So if we have car, goat, and goat, right? Here it is. Let's say we swap or no swap. So swap or no swap, swap or no swap, right? And so if you pick the car door, right, and you swap, so you have a 1/3 chance of picking the car door. If you pick the door with a car, then you have, well, okay, yeah. So if you swap to a car, let's say that's what it means. So swap to car or no swap. Well, okay, so, what should I say here? It's not really. So yeah, if you have, okay, so if you have a car door, that's 1/3. And so if you are shown a goat door and you swap, right, then you're going to get a goat. So the probability... Oh, I think that's basically... Yeah, that's how we have to do it. I understand now. Sorry, guys. I'm here. I hadn't expected to do the Monty Hall problem. So...
I threw you for a loop. I'm sorry.
It's okay. I got it now.
Because I knew you would get it.
Well, I didn't know I was going to get it. I thought I was actually going to miss it, but I think I've got it now. So this is the swap tree. And then we're going to do the no swap tree. And we're just going to look at the differences. Yeah, I figured the last proof out I figure a lot of things out on the fly. It's terrible. So, okay. Well, yeah, I do make that noise sometimes. So, okay. If you swap, then you have a 0% chance of getting the car, right? Because in the case where you pick the car the first time and then you swap, you're going to have a 0% chance of getting the car, a 100% chance of getting a goat, because you'll accidentally switch yourself into a goat door. If, on the other hand, you pick a goat door, right, and you swap, then you have a 1/2 chance of getting the car and a 1/2 chance of getting the goat, right? Because basically it's the same thing as if I show you one of the doors, right? If I say door C has a goat, then you're never going to pick that one. So swapping just allows you to pick amongst these two doors, and so you have a 50-50 shot now. All right. So the probability of getting a car, given that you swap, is 1/3 times 0 plus 2/3 times 1/2. Like that. Okay. So basically that is a 1/3 chance. So I think I might have done something wrong. That's very strange. Let's do no swap. And I've already written no swap. So if you don't do a swap, let's see what happens. If you pick the car door and you stick to it,
oh, it's the probability of the host opening a door.
The probability of a host opening a door?
Given where the prize is located.
So
if you choose door number 1, what's the probability opens door number 3? Well, if the prize is there, it's 0. If the prize is where if the prize is the door you picked, right?
Yeah.
So like so we look, yeah, because we're trying to figure out where the so if I pick a door, say I pick door number 1, what's the probability it shows me door number 3 given where the prize is located? And so it's if the prize is up behind door number 3, the probability is 0. And if the prize is behind door number 2, then the probability is 1. Then the probability is 1, and if the prize is behind what I'm pointing at, the probability is 1/2. And then you do your Bayes roll, I think.
So this says no swap, of course. So why the real question is not like what's the tricky way to look at it, but the real question is why is this wrong? Because all of these probabilities are correct, right? If you pick a car door the first time and then you swap, you have a 0% chance of picking the car and you have a 100% chance of picking the goat, right? Based on your swap. But I guess... And then here, if you don't swap, you pick... There's a 1/3 chance of picking the car door. And then if you stick with it, you have a 100% chance of getting it. Here, if you pick a goat door and you're shown another goat door, then you have a 1/2 chance of picking a car based on not swapping.
I think the issue here is that we're not factoring in like the probability that a particular door gets opened to reveal a goat.
All right, let's do a new page. So, I mean, you want the probability. So, what do you want to calculate? The probability of what? Given what?
I'm totally cheating.
I know, I know. So
we look at the probability if we stay on it, if we don't swap.
Yeah.
Then what's the probability of winning the prize?
If you don't swap? Well, so okay. Maybe so so I guess if you do a no swap, you could write a 1/3 on your tree, so this could be like a no swap. Right? Because you don't have a second decision. And then here,
well,
right?
Then we have the event of him showing us a door. Like showing us the goat.
Right. So the problem with the goat showing you the door is that he has to know which door has the prize. So, like, he'll never show you the actual prize door, right? Obviously.
Yeah, so the probability that he shows you the door, given there's a prize behind it, is 0.
Yeah.
And if you pick door 1 and the prize is behind door 1, then the probability of him showing you door 3 is 1/2. And if you pick door 1 and the prize is behind door 1, then the probability wait, no, I just said that. Damn it. This one's hard to explain.
I mean, I think the problem with the Monty Hall problem is that it's wonky. I remember being kind of unsatisfied with it. I think the way that the way that I think it's generally explained, right, is like if you have 3 doors, right? Then no matter what you've done before then, once they show you that there's a goat behind this door, right? Then the answer is and so they say the answer is always to swap, and the reason for it is that you have a 50-50 shot of getting it, right? Once you know that one of them the other one is a goat, right? Something like that. That's the explanation that's usually given, isn't it?
Yeah, the tree explanation is on the Wikipedia article.
Yeah, I'm sure it is.
You look at the probability that a car is behind a specific door.
Okay, let's see here. What do they say?
So assume that you just pick door 1, and then we're looking at the probability that after the host opens door 2 or door 3, what is the probability that you were pointing at a car, essentially?
Yeah, I mean, okay, so let's use the one on Wikipedia and then see if we can actually explain it. Because the tree I drew was clearly kind of either wrong or something.
I think you just have to take into account
the only problem is the only problem that I don't like is that this tree is not wrong. It's not wrong, but it tends to give you a wrong answer, which doesn't make any sense to me. So if you have door 1, door 2, door 3, and each one you have a 1/3 chance of winning, right? That we can totally buy, right? Yeah.
Yep.
We can buy that. Okay. So
say you chose door 1.
Yeah, okay. So if you initially pick door 1 and let's see, and they show you door 2, right? Okay.
So let's say it's
okay, wait.
The car's equally likely to be behind doors 1, 2, and 3.
Wait.
Okay.
All right. So what are they saying here? They're saying, so there's a 1/2 chance that they're going to open door 2 or 3. But that's not right.
Yeah, because if the prize is behind door 1 and you chose door 1, then it's...
Yeah, but they say given that you initially picked door 1, so we can't assume that the prize is behind door 1.
We're not assuming that the prize is there. We're saying that there's a 1/3 chance the prize is behind the door that I'm pointing at, and then the host, and then the second, that's the first probability, and then the second probability is what door he opens.
Right.
So then if we chose door 1 and the prize is behind door 2, then the only thing he can open is door 3 and vice versa. So it's a probability of 1 for those 2 second branches.
Yeah, I mean, okay. So now I'm completely turned around. Of course. So okay. So wait, stop.
Okay.
Don't turn me around more. I said I'm completely turned around, so I have to think now, which is unfortunate. So okay, door 1, and so there's a 1/2 chance that Monty Hall opens door 2. There's a 1/2 chance that Monty Hall opens door 3. Okay, and so if you pick door 2. And the prize is behind... I guess the prize has to be behind door 1 since they say there's a 100% chance they're going to pick door 3. And then it has to... So I guess we're assuming that we pick the right thing? But
no.
Otherwise it doesn't make sense.
No. The first D2 there is the prize is behind door 2.
This is the tree on Wikipedia, right?
Yeah, I know. Yeah. I'm saying... You chose door 1. That's not pictured here.
Yeah.
But the first D...
Oh, they can't pick... Wait. Oh, this is the car location.
Yeah.
This is not which door we pick.
Correct.
This is the car location.
Yeah, we picked door 1.
So that's a different thing, right? Okay, no. We can't assume that. So that's... So the Wikipedia... has an error on the assumption.
Ooh.
Right? Because you can't assume that... So you can either assume that the car is behind door 1 or that we pick door 1, but you can't assume both. Wait a second. So,
we're just trying to model sticking to our guns so that we pick door 1 and we stick with it.
Okay, so if the car... Oh, the car has a 1/3 chance of being behind anyone, and we're going to pick door 1, right?
Right.
So if we pick door 1, then there's a 1/3... Oh, wait, but we still... Okay, so... If he opens door 3... Okay. So what do we even do here? I guess you can kind of calculate this thing, but... No, but this actually doesn't give you the right answer. So if you... Really, we want the probability that we're going to pick door 1, because it's the probability that the cars... Oh no, that's where we initially are. Oh lord. What have I done? I shouldn't have agreed to do this problem.
What? But
yeah, this was a horrible.
No, but we're almost there.
No, this was a terrible accident because I've screwed up the explanation. I've drawn 3 trees that are wrong, and I've wasted 30 minutes of class time. So, yeah, it was oops. Crap. Unbelievable. I can't believe I shouldn't have done the Monty Hall problem unless I had it prepared because it's so wiggly. Like the problem with it is that you have to be really extremely careful.
Yeah.
And I thought I could do it just by a simple application of Bayes' theorem, and unfortunately, even here, 2/3 is not the calculation of anything on this tree, right? I guess you can say if the thing is behind, if the thing is door 2, for instance, like what is the probability of D2? Then
Well, no, you just.
nope, you don't get it that way.
What's the probability? Yeah. It's 1/3 times 1/2 plus 1/3 times 1/2. So it's basically there's only a third. Anyway, maybe Wikipedia is wrong.
No, I think so. I think the Wikipedia explanation is right. So now that we only have a few minutes left in class, let's go through it completely. So the car location is either door 1, door 2, door 3.
Yeah.
We will pick door 1. If we pick door 1, then there's a half chance that they're going to show us door 2. There's a half chance that they show us door 3, right? So if we pick door 1, but the car is behind door 2, then they must show us door 3, right?
Yeah.
If we pick door 3, the car is behind door 3, but we pick door 1, then they must show us door 2. So the probability, so let's think about it this way. So the probability that we are going to pick and then we are going to swap, right? So if the car's location was door 1, we don't get it. But if the car location was door 2 or door 3, right? And they showed us the wrong door, so it's door 2 or door 3, right? Is just equal to like 1/3 times 1 plus 1/3 times 1. And this pen is not writing. But, right? Because the thing is that if the car location is door 2, then they'll show us door 3. So if we swap, we're going to swap to door 2, which is right. If we pick door 1 and the car location is door 3, then they're going to show us door 2. So we pick door 3, which is right. But we're always going to miss it if we accidentally pick the car the first time. So yeah. That's kind of the explanation. It's a mess.
The other more broadly intuitive thing that I forget who explained it to me this way, but it made a lot more sense. If you had 100 doors in front of you and you picked a door, and then he showed you 9, and there's 100 doors in front of you, 1 car, and 99 goats. You picked a door, and then he showed you 98 goats. If you stayed on the door that you picked, you'd be an idiot.
Yeah, I mean, I guess it works out the same way, right? I mean, it would work out to be like if you had 98 of them, then or 100 of them, then you would just have like a bunch of these, and each one would be 1 over 100.
Yeah.
And I guess if he showed you all but 1, then yeah, each one of these would have a probability 1 of you getting the car. And here, what would it be if it'd be like what? I guess it'd be
1 out of 90.
It'd be 1 out of half, right? It would still be 1/2. And so I think you would just add up all those probabilities. Yeah, I mean, so the argument is that you should swap.
Yeah, the argument is you should swap. Because if you picked one of the doors and then he opened 98 doors to show you goats, then the chances are you're pointing at a goat. And that the one door he didn't open because there's a car behind it. So you should switch to that door. And so this is the same principle, is he's showing you all of the goats but one. And so the fact that he left a door closed when he showed it to you means that it's a bit more likely to be a goat. Or, sorry, the car.
Yeah.
So swap wins.
I should have
Swap
known
gets you
better
extra expense.
than to let myself get dragged into the Monty Hall problem.
Sorry, yeah.
Yeah, I honestly thought I knew better. I was like, I thought I remembered. The thing is, there's a difference between vaguely remembering the explanation and being able to teach it correctly. And we weren't there.
Yeah, we're not there. I'm sorry, buddy. I didn't mean to get you so sidetracked. It's a fun problem, though.
Sort of. It's really an infuriating problem. I think the issue with the problem is that, like, most of the time in a lot of these probability trees, you have to assume that, like, people don't have special knowledge at various levels.
Yeah.
Yeah, so the other it's an issue.
Are we gonna blast some womp rats? Do we have any womp rats today to blast?
No.
Oh.
I'll admit it, I'm annoyed.
Oh.
Yeah. My I mean, I wonder if you. So I think that there's there's a simple solution, right? And which we should have probably done from the beginning, right?
Yeah.
Which is like,
this is how they get their all night 203 stream. It's you and I going back until we're happy with our explanation.
well, I believe it or not, this is. Well, I don't know if it's.
Solve the trolley problem with Bayes' theorem. Yeah.
Well, that unfortunately requires some valuation on human life, which. So. Okay. So let's see. Goat, car. So what are the possibilities? You can either have goat, car, or you can have goat, car, goat, or you can have car, goat, right? And basically what you have to do using all of these possibilities is just go like, and there's a third chance of any given one of them. So that's right. So we can say that that's definitely correct. And I hope that's a reference to Changing Places, or Trading Places, which is a great movie. So then you basically have to say, if you pick door, there's like a 1/3 chance of picking any given door. So it's like 1/3 times, you know, you have a 1/3 chance of picking door 1, which would be a goat. But if you swap, so I guess if you don't swap, then it's a 1/3 times 0, right? Because you're not going to get the car. Plus a 1/3 chance picking door 1, which is, and so oh god, so let's calculate if we swap. So all right, so if we pick door 1 and it's a goat, then
the Bayes one's pretty elegant. Do you want?
No.
Oh, okay.
No, I don't.
Okay.
Let's see. Where's the Bayes theorem one? Definitely not.
Really? No, I have a link to a really good. Oh no, that's Reddit. There's no time for Reddit. Hold on. This is good. I put it in Discord. I'll bloop you in it too.
So, here's the problem with this problem. Depending on how you set up your tree, you get different answers. And so, unfortunately, the correct answer is that, like, you should actually do it out explicitly, and then you should probably run some computer simulations on it to prove to yourself that it's actually the right answer. Because this is one of those weird problems where, like, depending on how you, like, think about the problem, you write up a different probability tree, and that different probability tree produces a different result. And so
yeah,
it's...
I think this is the statistical thing of, like, is a plane on a treadmill going its takeoff speed in the opposite direction able to take off? And it's like everyone interprets the problem slightly differently, and then it makes it, it's, yeah.
Yeah, so here's the thing. If we pick door 1 and it's our goat and we want to swap, then what's going to happen is they're going to show us door 2, we're going to swap to door 3 so we get the car. If, on the other hand, we pick door 2, oh no, I'm sorry. Yeah, if we pick door 2 in this condition and we are shown door 1, we swap, we get the car. I see, that's where it comes in. Okay. And then if we pick door 3 in this condition, we get the car. They show us who cares what, we swap to a goat door so we don't get it. All right, so all of this together is what? That's 2/9 from that situation, right? And then we have another situation, which is this one here. But I think that the argument should be that they're all symmetric. So if we pick door 1, right, and we are picking the goat, but we swap, then we swap to, they'll show us door 3, we get the car, so that's yes. If they pick door 2, they'll show us either door 1 or door 3, but it doesn't matter. We'll swap to the wrong door and not get the car. Or, this I think is probably the simplest explanation and probably the best one in a sense, because this is definitely doing it for me. So, if you pick door 3, right, it's a goat. They'll show you door 1, you swap, you get the car. Awesome. So this is also a 2/9. And then the third situation is going to be symmetric. So if you calculate the third situation, it's going to work out the same, except it's going to be a 1/3 times 0 plus a 1/3 times 1 plus a 1/3 times 1.
I gotta say, you were being really hard on yourself, but I like this explanation, and you did figure it out. You came up with a new explanation I haven't even seen before.
I'm stealing this one also from Wikipedia, but they don't have the numbers all written out. So this is, I'm kind of like, I'm definitely stealing this one too.
But you're making it clearer than Wikipedia. Wikipedia got me more confused.
Yeah, so here's 2/9 plus 2/9 plus 2/9, which 3 times 2/9 is 2/3, which is the answer, and we can be done with this problem. So there are some explanations that involve conditional probability, but I suggest it looks horrible.
Can you prove that you are the goat?
No, I'm certainly not the goat. If I was the goat, then I would have done this from the start and not done all the extra crap and failed 3 times, and yeah. So yeah, awful. Terrible.
No. Wonderful. We did it.
No, literally the worst.
No. No.
Um,
no.
Yeah.
All right.
Yeah.
I think this was good. I like this. I like this problem.
I wholeheartedly dissent.
That's okay.
Yeah,
That's okay. I think we're past due for our outro, our lo-fi.
Yeah.
Yeah.
Look at all the problems that we didn't get to.
Oh no.
I might actually do another session where I just do some of these problems, and that way I will feel less like a failure.
And I won't interrupt you with.
Well, I'll just do them myself. It might not even be a stream. I might just do it tomorrow. That was hard. That was hard on me. And of course, it had to be the Monty Hall problem. Because, like, I was too arrogant and too late, I realized.
What would you rather have, though? A $30,000 car or $30,000 worth of goats?
$30,000 worth of goats.
Really? You take the $30,000 of goats? What would
Yeah, you know why? Because goat prices don't depreciate like car prices do. You buy a $30,000 car, it's only worth $20,000 once you drive it off
Well,
the
what if I
lot.
said it was a 30,000? Like you could turn around and sell it for $30,000. I guess that kind of makes it pointless because then you could just sell the goats for $30,000.
Well, yeah, goats can almost increase in value. Plus, you can almost breed
That's
goats and
true.
have more goats. You could become a goat
That's right.
farmer.
Then you get more goats. In a couple of years, you might have $60,000 of goats.
That's
The
right.
thing is, you have to invest so much in your goat infrastructure.
Um,
I guess you could sell like half of the goats immediately to pay for all of the like no, because you need a lot of land for goats, and goat land is more than $15,000, right?
well, it depends where you're buying it, but yeah, I guess.
That's true.
I mean, look, I guess if I were going to be given the option, I would probably. I mean, it depends on how much effort you're willing to put in. I guess I might go with a car just because it's. Even taking the $20,000 from the depreciation on the car is better than having to take care of goats. Because I honestly know nothing about taking care of goats.
Here's what you
So-
can do. Here's the real move. You take the car for $30,000. You immediately sell it for $30,000. Then you buy $30,000 of goats.
And you feel like a winner, I guess? I don't know. What's happened?
Then you live both those lives.
Yeah, I think the right answer is take the sports car, sell it immediately, and then, I don't know, go live under a rock.
I mean, a sports car isn't even $30,000. Let's be honest.
Well, it depends what kind of sports car.
I guess if it was, 30,000. Sports cars are pretty expensive.
Yeah, if you're talking like one of the high-end
Yeah.
sports cars, then yeah.
Yeah.
I mean, granted, if it's a 30,000, if it's a 90, I guess that's a question. Would you rather have $1 million sports car or $1 million worth of goats? See, that's a different question than 30,000 because, like, say a goat is like $300, so like $30,000 of goats is 100 goats. But say I offer you $1 million in goats. Right? That's not 100 goats. That's like what? 3,000 goats?
Yeah, that's a lot of goats.
I mean, or something around there. So that's a ton of goats. It's like 33,000 or 3,300 goats or something like that. You're gonna be swimming in goats, man.
Possibly, literally, that's a lot of goats.
Yeah, I guess. Yeah, that's a good point. If you got $1 million in goats, you could sell half your goats and then buy land for the other half of the goats, and then you would have a goat farm and then raise the goats.
How much is
get yourself a sports car?
I want to know. I want to just buy a goat. I hope.
The goats range in price from $75 to $300.
Oh.
Supposedly.
Goat pricier.
Apparently, sex, age, and temperament.
I see. Isn't that always the way?
Okay, so a neutered goat is cheaper, typically around $100.
More goats. Yeah.
Yeah.
So I'm thinking, like, if you have all these goats, I'm also hoping that some sort of like the speech to text and stuff starts to, like, when students stop watching your stream, they get all of this like farming stuff. Like, I'm hoping that we're just saying goat enough that they're gonna get,
it's gonna have like a hashtag goat farmer underneath.
Yeah.
Like that's literally the point of this entire lecture.
Mm-hmm. That's what I say when 341 students are in my office and they're particularly frustrated. I'll just look around and be like, why don't we all just become farmers? It seems like it's a lot less logic there. It seems like more work though.
You know what the sad fact is? Freaking Monty Hall problem. I
feel so bad.
I'm gonna come into your lecture and derail you.
No, the problem is you came into my lecture with stuff like that. It would put me more on track. I would actually talk about one's particular thing.
See, my idea was that this was going to be the last conditional probability Bayes theorem lecture, and then I would do some. I wanted to start graph theory on Wednesday.
Ooh. Oh, I put off graph theory? That's terrible. I love graphs.
Well, as I say, I'm probably gonna release like some extra things, example problems, and then I'll just start graph theory Wednesday anyway. Because graph theory is more entertaining. Like, I will say Bayes' theorem is like extremely useful, unless of course you're sitting around trying to trick me with the Monty Hall problem. But then I like that on the Wikipedia article there's actually like there's like research still going into it. Like people are publishing papers on it even into the 2010s.
Because nobody believes that the answer is the answer, you know?
Yeah, I mean, I guess the right answer in life, right, is what you do is you create
A simulation.
yes. Because you don't believe anything, and you think that the world is chaos.
Yeah.
Now, of course, the real question is, what is randomness? And the answer is unknown. But anyway, what we can do is we can just go like, well, okay, so let's say the door is equal to choice, random.choice. Actually, we could just do random. I think 1 to 3. There we go. And then what we can do is say, let's see, 4 trials in range, say 1 million, or n. And so how do we model the problem in coding? We basically say, here's the correct door, right? And so that now we're going to have the picked door. Random.
We don't have to model staying, right? Because that's obviously going to be a third. Because
is it obvious?
Maybe not, obviously. All right.
Let's pretend like it's not obvious, because as soon as you say something is obvious, then I know that it's not obvious.
Is that just me or
No, it's a fundamental theorem of mathematicians. As soon as a mathematician writes or says the word obvious, then it is not obvious and you need to check. So, let's say swapped correct equals 0, non-swap correct equals 0. And so what we're going to do is if picked door, yeah, okay, so it's going to be a third, right? Then non-swapped plus equals 1. And then, let's see. So if the correct door was not the picked door, so how do we model the swapping business, right? So if, how do we swap?
We should have just coded this from the start. I think it's just going to be like obvious now and we're going to feel dumb. All right.
So if the pick door is the correct door, then we don't get it. Else, if the pick door is not equal to the correct door, then we have so how are we going to code this?
Okay, so if the pick door is equal to the correct door, then the swapper's going to lose.
Yep. So non-swap or swap correct is 0. Else,
well, don't you want plus equals 0?
yeah.
Otherwise, then we just.
So what that means is that it was not equal. So what we're going to do is the Monty Hall door, right, is going to be of one of the wrong doors, right? Oh, but we already know that it's going to be one of the wrong doors, right? So swap correct plus equals 1. Does that make sense?
No.
Because
Wait.
if the pick door was not the correct door, right? Then what's going to happen is they're going to pick a goat, and you're going to swap the
Yeah.
and you're going to swap into the right one.
Oh my god, this is the best explanation I've ever heard. We won.
No, we didn't.
We won. They should give us all the goats.
No, we didn't. Don't even lie.
You don't think we've won?
Oh. Hell no.
How many Oh, we're going to input n. Oh, we are.
Boom. So that just approximated 2/3, 1/3, didn't it?
Yep.
But we kind of have to. You kind of have to argue this, right? You kind of have to have a comment here that says like, if the else. So this means the pick door is not correct. So Monty Hall is going to show us the wrong door, another wrong door, right?
Yeah.
And so we will accident ourselves into the only door left, which is correct.
That's a good comment. This is the clearest explanation, though.
You think so?
I think it's, yeah.
Yeah, maybe. Because, like, let's run 10 million trials.
So what are these recent papers about?
I'm not sure. I think it's just alternate proofs.
Oh.
So, yeah.
There's also just, like, letters to editors of things. No, but
letters to editors. Good. I mean, that's...
See, this is why I just, if I can code up the maths, then it makes more sense. This is good. But see, we didn't completely waste I didn't waste all of our times.
Wow, look at that. Look how close to 2/3, 1/3 it is.
Wow, damn.
It's pretty close. I mean, of course you could say it's infinitely far away, but it's pretty close.
Yeah.
Yeah, I mean, it's not bad.
I mean, we are just basically counting how many times.
Yeah, now that we know that this is...
Two random numbers between 1 and 3 of the same. Yeah.
Yeah, and the else statement is this, so...
The else statement is fancy, because if the two are the same, if the door you picked was correct, then not swapping means you're right. But that's only going to happen 1/3 of the time. Whereas Monty Hall is going to force you to pick the correct door if you swap, if you happen to be wrong. And that means that your 2/3 chance to be wrong has now become a 1%. Like, now you're going from being in the minority of being right to being in the majority. It makes sense. This is so good. This is the best explanation. We did it. We did it. We did it, Eric. Not we. You did it, because this was entirely your idea to program it out.
I mean...
So wait, okay, hold on. This is so good. This is so much more succinct.
Oh god.
Oh god.
Yeah, you see, like, so those, I hate to say it, but the Monty Hall problem, the way it's worded, is kind of a trick problem. Everything about it is a trick problem.
It's totally a
trick problem. It doesn't, it's bad. But on the other hand, there is apparently a quantum Monty Hall Python project, so quantum Monty Hall problem. So I'm not sure exactly what that means.
This is peak math. Post this on GitHub.
The 3 doors are replaced by quantum system, allowing 3 alternatives. Opening a door and looking behind it is translating. Oh, to making a measurement. The rules can be stated in one language, and so once again, the player's choice. Okay, to choose another orthogonal option. The latter strategy turns out to double the chances, just as in the classical case. However, if the show has not randomized the position of the prize in a fully quantum mechanical way, the player can do even better.
So we're talking about quantum mechanical goats now.
Quantum mechanical doors, really. Like, the thing about, yeah, so it's like if you make an observation, it's the whole thing about like collapsing the wave function business. Yeah.
Schrodinger's goat. All right, I should go eat. We should go eat. This was fun.
I mean, define fun. But yeah, maybe I will post this on GitHub just to troll the students. I'm sorry, everybody.
I'm sorry. It's my fault. I shouldn't have brought up Monty Hall.
I make mistakes. I had a thought, and I was like, oh yeah, I'm completely prepared for what is about to happen because I've gone through the Monty Hall problem, like, and now I realize what the problem is. I went through the Monty Hall problem 8 years ago.
Yeah.
And I still had a memory of it, which made me
you derived it on the fly. That's so.
Which made me confident in a way that I should not have been confident. So yeah, I shouldn't. Yeah.
But we got it. Reddit. All right, I'm gonna leave you alone. I feel like I've made you miserable. I apologize.
Well, isn't that the point of life?
To make you specifically miserable, or just to?
Yeah. No, I feel like there's an inverse relationship between like my misery and the relative well-being of mankind. So it's like one of those things where it's kind of like this. Where is the pen? It's like if mu stands for misery, it's like misery of Eric times the misery of the sum total of all mankind.
Sometimes when I write problems for homeworks,
is some constant. So unfortunately, it's a problem of utilitarianism, right? Because if you sum up, over mankind, and you want to take the derivative over d people.
Is this formula showing that me picking on you by invading your class and hopelessly derailing you with goats means that I'm doing charity work?
Yes. What you're trying to do here, utilitarianism can be summed up in this formula here. The derivative of this equation is 0, and then you want to seek to minimize the misery function, or alternatively maximize, say, the utility function. Now, of course, you kind of have to assume that the utility function is like linear on people. So like the utility function on like person 1 plus person 2 is equal to utility.
But what about
of person 1
distribution of Eric's
plus person 2? No, this is specifically me.
No. I mean distributing you across humanity.
Well, no, I mean you wouldn't want to do
Eric inside.
Yeah,
so
I mean,
if you make an Eric miserable, it's all of our every human's like little niche corner of Ericness is sad, and that's so it's actually.
Well, again, I mean, we have to assume some kind of independence of like what my well-being versus the independence versus. I guess this is like. The set of people, minus.
Thing. What if? I mean, not just what if. It's got to be the case that everybody has a bit of Ericness within their moral being.
Sure. I mean, everybody might have a part of my personality, but that's not to say that This is to say the misery of the specific conscious entity, which is me.
Uh-huh.
Right? That so their misery is completely independent. I would hope.
What about third? Okay. Well, what happens to the utility of all this if we give you $30,000 of goats?
Oh. Well, you see, there's a special term here. I call it lambda for, the number of lambs or goats you have. And yeah, so there's there's a cosmological constant that is related to the number of goats. Oh, the cosmological constant even takes g. So
That's what it is.
So actually, yeah, I mean, normally the relativists all believe that g stands for the metric defining spacetime, but we know better. It's actually just the number of goats. So yeah, so actually, there is quite the merit to this. I think this equation is getting truer and truer.
So are we? Oh gosh, does this mean that now you have to be personally responsible for goat proliferation?
Oh, actually, maybe we could put a minus sign in. Oh yeah.
Did we determine that you have some sort of goat moral imperative now? Or are we about to actually prove that you are the goat? I feel like if you multiply both sides by goat over goat, we just get Eric times goat.
Oh no, this term is hopefully hopefully a function of goats rather than just being a linear, rather than just being lambda times g.
Goat is Eric spelled backwards if you change all the letters in their ordering.
That's correct. There is a quite distinguishable permutation of letters that takes you from, you could say like sigma of goat is equal to Eric.
Yeah.
Now, the distinction here is that there are quite a few problems, but whatever. Just call it like an isomorphism, right?
So I almost said if you added or subtracted 2 places from each value of Eric, you'd get goat, but you don't. That I is too far away.
I'm sorry.
J, K, L, M, N, O. No. I've never been high before, but I feel like class is what being high would be like. Maybe, I don't know. Yeah. If you think being high is like being blissfully confused.
Yeah, I mean, how many times have we written down these utilitarian derivatives?
We do it all the time. Woo!
I know my dog's not happy with whatever that was. I think it makes her a little anxious when I keep my door closed.
Yeah, Charlie gets upset, but he doesn't have much say in things.
Yep.
Except he's cute, so he has all the say in everything.
Alright, well, I'm gonna go and work on the project and get that done, and then eat food. Or maybe eat food and then do the project.
I had fun, unfortunately, at your expense.
Yeah, my expense. Oh, and my poor students.
They seem to be enjoying themselves.
Yeah,
They got to...
I just take it much harder than they do. Like,
the problem is you think
I view it as a personal failing, which it is.
You think you've been exposed to some sort of fraud,
and I have been. Look at that.
All the rest of us mere mortals are sitting here like, how did he actually figure it out 4 different ways in one sitting?
Well, I had to cheat.
That's your... Oh, please. No, you didn't. You silly man. See, we're all in all. You're like, gosh, my brain is not working at full universe, galaxy, quantum go.
Oh man, it hasn't been doing that for years, man.
We're sitting here like
I'm operating on
hope he draws another goat. The rest of us are just like, those goat drawings.
Hey, at least I redeem myself by doing the proof without any screw ups, and I gave a good explanation of Bayes' theorem here
No,
with
man,
with
I'm
the
telling you,
with the
you on the
sausage.
fly took on the most counterintuitive problem, and you killed it.
I wouldn't. Let's not even come close to saying that.
No,
I
fine.
was.
You know what? You're terrible and awful, and I'm
I
getting
like
to know
this.
you.
It makes me feel
Yeah,
better.
you're
That.
bad. You're bad. You don't even you don't even clap along to the greatest hits albums.
Oh, nice.
You don't double bag produce.
You know I
No.
don't.
Yeah. You have
If we put a billion goats on typewriters, eventually the one would type Eric. Oh, that's a great thing to do. Oh, perfect.
what's the expected number of typings to get Eric out?
Yeah, well, no, here's what we do.
Are we doing like entropy sort?
We're going to have, I'm going to start it now. We're going to call this, and then what we're going to do, before I go, this is the last thing I'm going to do. Okay, and then let's just have n for the number of monkeys. Or maybe goats, typewriting Eric. And so, let's make my life easy. Okay, so now what we're gonna do is we're going to have while that's a good question. Okay. Goat strings. There we go. For while all goat strings I let's see, -4 to the end is not equal to Eric for I in range n. Yes. Random dot choice. Cool. For I in range n. This is such a troll. Okay. Goat strings I
This is
plus equals
some seriously dense Python here.
and at the very end we'll print out no strings. Okay. Yeah, I mean, this Python I think is so let's make 10 goats.
10?
Yeah. Why don't we print it out every time, just so that things will be absolutely the most chaotic thing imaginable.
Oh no. This is gonna take longer to like print to the screen.
Yeah, I feel like we should take
It's also
out
doing the same thing over and over again.
Yeah, that's very strange. Why is that doing all of Let's
Clear out the...
It terminated.
Did it really?
Yeah.
What?
All right. Oh. Now I have to find Eric. There it is. Wow, a goat typed Eric really quickly. All right. Let's make it a little harder for it. No.
Oh.
Oh, wait,
Okay.
but we can't have spaces because I don't allow it to have spaces. I think this might go on forever. So what's the probability of this? The probability that a goat types Eric in n characters is 1 out of 26 to the power of 47443, so that's 11 to the power of 11. Oh, Lord.
Is it more than 12? Eric.
It is 2.72 times 10 to the negative 16th power.
Okay, so what was it for 4?
Let's calculate.
Somebody came back and said, is it still going on? I left for 20 minutes.
Times 10 to the minus 6. So that, given a million operations per second, we should expect to complete within about a half second, which is what happened, right? It terminated really quickly. But this one, on the other hand, is not terminating very quickly. Let's give it a little bit of a benefit of a doubt and like make it just Eric Goat. That way, it might terminate within our lifetimes.
We could get lucky. It could just immediately spell Eric Goat.
Times 10 to the minus 12.
Do it, Eric Goat. Eric Goat. Eric Goat. Go. Go. Run. Oh, is it still running?
Yeah.
Oh, I didn't think you would hit it to go.
Yeah, no, okay, so what is the expected, if we take the reciprocal of this number, and we divide by 60, divide by 24, approximately 2.4 days.
That's our expected goat, Eric Goat value.
Yeah, I guess I'll just leave it running and see what happens.
Gets 5 degrees warmer in the room you're in.
Oh no, I mean, God, I shut the door in here, and my computer, even when I'm just lecturing, it pumps the temperature up to like 80, 90 degrees. I sit here and I sweat. It's actually terrible. Yeah. During the summer months, it's going to be real bad.
Mm-hmm.
Did I create a Bitcoin miner? Thank God I did not. But, yeah, so, wow. Isn't that beautiful code?
Yeah, I would.
Oh, wait.
If you were my coworker, I'd yell at you.
There's a bug.
Oh, it would never.
We had to restart it.
Watch it finish.
Watch it start. Watch it finish in the next like 10 seconds. We should just make a separate stream, like its own YouTube channel.
Oh.
It just watches this code and just is like, done.
In search of Eric the Goat. Yeah.
Yeah. I mean, oh, that would be awesome if this finished. You would yell at me for this code? This is beautiful. I would yell at you.
Yeah.
This is the best.
I'd say you're a loose cannon, Hamilton. Now hand in your rubber ducky and badge.
Man. Can't believe it. This is baby stuff.
Oh, I'm not saying it's too advanced. I'm saying it's too, like, impenetrable. It's not easy to read. But that's okay. That's okay. It's okay, because we're getting some goats.
Yeah, but you can read this. It's 100% readable.
All right, I'm gonna go eat dinner. It's late.
Yeah. Also, this is gonna literally take 2 days. And that's the expected time, right?
Yeah.
So it could take the probability that it takes twice the expected time is not 0. It could take multiple days. Anyway, all right, it is dinner time for all of us. Okay.
All right, bye-bye. Bye, everybody. I miss you all. I miss you most of all, Eric.
I know.
Even though we talk to each other all day.
I know, it's terrible, really.
All right, have a good night. Bye.
All right, bye, guys.